All right, so this evening we're going to be looking at vertical projectile motion graphs. Now, before we get onto vertical projectile motion graphs, I'm going to be starting by looking at just general graphs of motion. And once we've done those, we're going to look at the specific examples with vertical projectile motion. All right. I'm busy getting very entertained by some of you at the moment. It's awesome. It's awesome. I hope you know you make the video cut too. Awesome. All right, so I'm going to just quickly try and get everything set up. All right, everybody's in and we can get started. So I warned you when we did this, when we looked at this last time, that I tend to slightly overshare this section. Well, not overshare, overteach this section. So we're going to be looking today, and I apologize, I'm going to be drawing graphs and they're going to be very squiggly, but hopefully you'll have the general idea. Sorry, there we go. Okay, so I'm going to be looking at graphs of motion. Okay, and when we look at graphs of motion, it's very important for you to understand, this is now me teaching you grade 10 graphs of motion, that within the section of graphs of motion, there are actually 9 different graphs you can get. You get 3 types of graphs of motion. You will get a displacement versus time, a velocity versus time, and an acceleration versus time. And then there are also 3 conditions of motion, which are that we could be accelerating, we could be moving at a constant velocity, or we could be decelerating. So because there are 9 in total, I tend to represent this by starting off almost taking a step back and saying, here are the 9 possible graphs that you could end up getting. So I'm just going to make sure I do this correctly because I've had a week of being silly about these things. So here's my displacement versus time. There is displacement versus time and displacement versus time. Strongly suggest that you take a screenshot of this, or even better, you try and draw out your own while I'm doing it. But I may be going a little bit fast, so you may need to come back and copy down details afterwards. So everything in this row is going to be velocity versus time. And last row is going to be acceleration versus time. When I draw acceleration, it's the only one where you've got both a positive and a negative y-axis. Okay. So that is the basic setup. So hopefully everybody can see here that there's 1, 2, 3, 4, 5, 6, 7, 8, 9 graphs representing the 3 types of motion and the 3 conditions. Everything here is about displacement, velocity, and acceleration. Then going downwards, everything here will be dealing with motion that is accelerating. Here it'll be motion that is traveling at a constant velocity. And the last column will be for motion that is decelerating. Some people view decelerating as a negative acceleration. I don't really mind which way around you view it, as long as you appreciate that both are equally appropriate. All right, so if an object is accelerating, its displacement versus time graph will end up looking like a smiley face. Okay, we can call that concave up, but I'm good with smiley face. If the object is traveling at a constant velocity, we will get a straight line. And if it is decelerating, we will get a sad face. Please bear in mind you actually get both sides of the smiley face and both sides of the sad face depending on how your displacement is changing. Now, I find that the easiest way to picture why this happens is for us to imagine that we're looking at equal time intervals. So for example, I may say there's 1 second, 2 seconds, 3 seconds, 4 seconds, and 1 second, 2 seconds, 3 seconds, 4 seconds there. 1, 2, 3, 4. Okay. In my first second here, that is how much displacement I have. It's tiny. In the second, I've covered a little bit more displacement. By the third second, I'm covering a lot more displacement. if I go up here, by the 4th second, I'm actually covering quite a lot more. So you can see that this object is accelerating because there will be an increasing displacement in successive time intervals. Okay. Over here, when we're traveling at a constant velocity, if you draw this, and please, if I'd drawn it neater, you'd see that's a little bit more effective, but you get the general idea. Here, if we're traveling at a constant velocity, we will cover the same displacement in successive time intervals, which makes sense. Constant velocity, you're not speeding up or slowing down. You're going to cover the same displacement every second. So here we will have the same displacement in successive time intervals. If, on the other hand, we're decelerating, we're slowing down, so here we would have covered a huge displacement in the first time interval, a smaller displacement in the second time interval, a smaller still displacement in the third time interval, and a smaller still displacement in the fourth time interval. So here we will have a decreasing displacement in successive time intervals. You'll understand why I'm going through all of these things once we bring it all together, but for now I'm just going to ask you to trust me. I do know where this is going. The next thing that we look at is how will our velocity graph look? If we're accelerating, our velocity graph will be a straight line with a positive gradient, because as we're accelerating, our velocity is going to be more and more and more, okay? If we're traveling with a velocity that is constant, it will be a horizontal line. Now that's not very horizontal. I'll try and make it, there we go. That's more horizontal. Please note the bottom line is the problem. And if we're decelerating, we will have a straight line with a negative gradient. So with all of these velocity graphs, they are straight lines, but here we have got a positive gradient sloping upwards. Here we have got a horizontal line. And here we have got a negative gradient. That kind of makes sense if you think about what we're looking for when something accelerates, moves at a constant velocity, or decelerates. If we're accelerating, our velocity will go higher as time goes on. If we're traveling at a constant velocity, the velocity will remain the same as time goes on. And if we're decelerating, the velocity will decrease as time goes on. All right, I'm just quickly double checking that everybody's good with that and there aren't any questions. Okay, brilliant. Then we look at what our acceleration graph will look like, and I'm going to change colors here so that you can see it clearly. If we're accelerating, we will have a horizontal line that is above the x-axis. So basically a positive acceleration value and a horizontal line. If we are having a constant velocity or zero acceleration, the line will line on acceleration is 0. And if we are decelerating, it will be a negative line. Now, unfortunately here, this is very funny because my lines themselves are not straight. It's a bit of a mission to see in there. All right. So, ladies and gentlemen, can I ask you to just quickly take a screenshot of these explanations? The shape of our displacement is either smiley face, straight line, sad face. Velocity will always be a straight line. Acceleration has a positive gradient, deceleration, negative gradient, constant velocity, horizontal line. And with acceleration, they're always all horizontal lines, but what changes is whether they're a positive value, a zero value, or a negative value. All right. Can I quickly ask, because I don't want to lose any of you, did this all make sense to everybody? Thumbs up if it made sense and you're still with me. Okay. All right, fantastic. Okay. Just quickly checking, there was one question here. All right. Would you ever be asked to draw a velocity time graph when the acceleration is increasing? They're not supposed to be able to test you on a changing acceleration. So our assumption in all of the graphs that we do is that acceleration is constant. However, we can change from one acceleration to another acceleration, and the way that you draw that is you actually have one horizontal line at one value and then another horizontal line at a different value. But you'll never end up with an acceleration where there's actually a gradient in between. It'll be from one instantaneous to the other. A little bit like when you're driving in a car, you can go from constant velocity to acceleration, but you'll be able to do so by my foot is not on the pedal, my foot is now on the pedal. So because you'll be able to change from one acceleration to another instantaneously, our lines will be two horizontal lines that are joined with usually a dotted vertical line in between. Sometimes, if we're being accurate, a slightly diagonal line, but we tend to make it dotted either way because we're not dealing with a changing, or we're not dealing with the rate of change of acceleration. We deal with constant acceleration. All right, so that was the first bit of this. There are two little bits, and then we link it all together, and then I want to link it to vertical projectile motion. I know I'm going a little bit fast through this, but there's a lot to cover, and I don't want to take more than half an hour to get through the basics. Okay, so the next thing that we're now going to look at is how do we link our displacement our velocity, that's just a V, and our acceleration. How do we link these three concepts, quantities, or even graphs to each other? So I'm going to link going downstream first. So I'm going to remind you that the velocity is the change in displacement over the change in time. That means that if I have got a graph of my change in displacement versus my change in time, let's just pretend it's like this. If I'm looking at the change in displacement, which is on my y-axis, over change in time, which is on my x-axis, I can actually say that the velocity of a displacement versus time graph is determined by looking at the gradient. So if I want to figure out what the velocity is of a displacement graph, I can look at the gradient at any point. Similarly, acceleration is change in velocity over change in time. So if I've got a graph over here that is velocity versus change in time, and I look at the change in velocity, change in y, over change in time, change in x, once again, that's my gradient. Please, just a little note, we haven't done very much on graphs up till now, but it's very important that you realize that this is science, this isn't maths. And if you ever talk about gradient being y2 minus y1 over x2 minus x1, you're not going to get all of your marks, okay? In fact, we don't give you a formula mark for that. What you'd have to do is you'd have to say gradient, and it's full worked out gradient. It's not m. And here, if I were looking at change in displacement over change in time, I could say x1 minus x, or x2 minus x1 over maybe even delta x, putting it formally, over t2 minus t1, and you'd get a formula mark because you were using an appropriate gradient for the physical quantities that you've got. Please be very cautious. I know in the Western Cape, we do not give marks for gradient in that format. Okay, it's got to be written out instead in terms of the variables that are involved. So to get from displacement to velocity, we look at the gradient. To get from velocity to acceleration, we look at the gradient. If you think about your maths and your calculus, this gradient is the rate of change. So velocity is the rate of change of displacement, and acceleration is the rate of change of velocity, which means that every time we're looking at our gradient, we're effectively dividing by time because we're turning it into a rate. That's one of the reasons why displacement is in meters, velocity is in meters per second because we've done it as per unit time, and acceleration is meters per second squared because it's meters per second again. And the per second again becomes per second squared. If we were to go backwards, we're now going to rearrange this equation. And we would say, well, displacement is actually velocity multiplied by time. So if I had a graph here, I'm going to make it an ideal graph that's very convenient for me. But if I had a graph here that's velocity versus time, velocity versus time is area under the graph. So for me to go backwards from velocity to displacement, I will look at the area under the graph. Similarly, if I look at a graph of acceleration versus time, and please note this could be positive or negative, it doesn't really matter. But if I want to know what the velocity is, I'm going to look at the area under the graph as well. So to go backwards, this is going to be area under the graph. And the reason that it's that way around is over here, we would say that our velocity is equal to our area multiplied by the change in time. All right. So the easiest way for me to actually teach this to you, and yet again I'm repeating, I am teaching this in way more detail than it's ever going to be examined, but I find that if you can do what I'm about to do with you now, there is no question they can ever give you that gets overly confused because you fully understand how to move from one graph to another. So I'm going to give you a picture of a velocity time graph, and I'm going to ask you from it to draw the displacement time graph and the acceleration time graph for that same portion of motion. Because I don't want to take too long on this, I'm not going to make it an overly complicated graph. I usually, for my poor grade 10s, give them about 8 portions of motion. We're probably going to do, let's make it 5 maximum so that we've got enough time. All right. Can I ask everybody to just quickly take a screenshot of anything that they want from that before we jump in? And just quickly, I'm going to actually cross that out. You don't want to use that one. That's not the one you want. All right. So I'm going to quickly clear my screen. I'm going to stop sharing and I'm going to say, first of all, does this make sense to everybody that's here? Are we understanding sufficiently well what we need to understand? Okay, good. Good, good. Perfect. All right. So let me continue sharing. Okay, I'm going to try and make this as neat as I can. I'm not promising very much. I'm trying to do this faster rather than neater. Okay. So, yeah, it does actually tell me when it's horizontal and it's not liking me at the moment. There we go. Okay, so imagine that we had a graph here which went up a bit, across a bit. It'll look a little bit like Table Mountain by the time I'm done. Down a bit. Okay, and then because I want you to work with negative things as well, not that far down. Down a bit more. Sorry, it'll do funny things if I don't let this do one step at a time. And then up it again. Okay, let's just make this one longer. Where is that one? Okay, a little bit longer. All right. I'm going to make this a little bit longer as well so that everything fits on. Imagine that I then gave you particular values for here, and I told you that this was, I don't know, let's make that 5. This is velocity in meters per second, and this is going to be time in seconds. Let's make this value here go down to -2. My time here could be 5 seconds. My time here could be 10, 12, 14, and 15. So this is a completely random little graph. Basically what it describes is an object that's first of all moving forwards and speeding up, then continuing to move forwards but at the same speed of 5 meters per second, then slowing down over a time of 2 seconds till it temporarily comes to a pause, not a stop. Then it turns around and goes backwards, speeding up, and then it continues going backwards but slowing down and stopping. So everything here that's above the graph on a velocity graph is us moving forwards. Anything below is us moving backwards. But very importantly, backwards from the furthest we got away, not backwards from the start. So if you've been going forwards, 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 and then you turn around, you don't suddenly start here and start going back from where you started. You start from wherever you've ended and you go backwards. So we're going to start off by drawing the displacement versus time graph. And you must remember that this is using cumulative area under the graph. Okay, please, I'm going to do all of this rather quickly because I think I've emphasized enough that I'm worried about time. So I am going to lay this out. Every one of the portions where anything changes, I have to treat separately. So I'm going to do 0 to 5, 5 to 10, 10 to 50, sorry, 10 to 12, 12 to 14, and 14 to 15. Even if this line looked like it was a straight line, I find that whenever I go through the velocity of 0, I treat it as a new section because the graphs aren't always drawn to scale. So my displacement from 0 to 5 seconds, I'm looking at the area under the graph. Over here I have a triangle. So I would say it's a half. My base is 5. My height is 5. So a half times 25 tells me that I will cover 12.5 meters in the first 5 seconds. My displacement from, where are we? My displacement from 5 to 10 seconds, this shape here is a rectangle, so it's going to be 10 times by 5, which gives me 50 meters. Please note, at 10 seconds, we are not 50 meters away from where we started. We got 12.5 meters forward as well as 50 meters. So I do a cumulative total where I say my displacement at 10 seconds is actually going to be 62.5 meters. You must remember this bit of being cumulative area happens here. If you move forwards 12.5 meters here and 50 meters here, you can't suddenly be 50 meters from the start. You've got to add the two together. Okay, continuing on, my displacement from 10 to 12. Yes?
Sorry, ma'am. Is the base of the rectangle not 5? So it would be 5 times 5.
Thank you. Perfect. Long day. Yes. Please correct me on these things. I know I make mistakes, even when I'm wide awake, but late at night more so than usual. Thank you so much. So 12.5, thank you, plus 25 gives me 37.5. Please don't ever feel afraid to correct me. I'm much rather that I didn't have videos that were complete nonsense. All right. Then over here, we've got a triangle. So it's going to be a half. My base is 2. My height is 5. So that's 5 meters. Cumulative displacement by 12 is therefore going to be 42.5 meters. Okay. Then, because our displacement goes negative, we're going to have an area that is also negative. So just bear that in mind. My displacement from, where are we up to? We're up to 12 to 14. It's still a triangle. So it's going to be a half. My base is 2. My height is -2. Those cancel, so it gives me -2 meters. And what you'll see happens with my displacement is that we're going to add -2 to that value. So we're going to have turned around and we'll have less total displacement from where we started. And then lastly, from 14 to 15 seconds, it's also a triangle. My base is 1, my height is -2, so that'll be -1 meters. So overall, my displacement by 15 seconds is going to be 39.5 meters. Just something I always have to add in. I don't know why my grade 10s always get fussed about this. That is 0 to 5, not 0 minus 5. That's just my shorthand saying it's from 0 to 5, 5 to 10, 10 to 12, etc. All right. Now what we're going to do is we're going to quickly plot this graph. I find that if you can plot the graph, you're sorted. Now, before plotting the graph, look at your cumulative. If you were trying to plot the non-cumulative values, quite often your things go big, small, negative, and they kind of look like, I don't know, those sound, I guess you could view them either as being sound coming out of a speaker or even a skyline of a city. There's no pattern to it. So you must always check that you have actually remembered to do cumulative values, or you're going to end up with things that look like nonsense, literally. All right. So yes, please, if you got, okay, now there was a question here about, could we work out the area of the trapezium instead of dividing the shape? not for this particular activity, because I'm aiming to plot a very accurate graph where I need to know what's happening at 5 and 10 and not just at 12. If the question here had been, what is the total displacement in 15 seconds? You could have jumped straight to the end answer by just literally having that plus that plus that plus that plus that. So the reason I've done every single individual shape is I want the little nuances in my shape for my overall graph. Usually they don't make you plot the graphs. You don't necessarily need to know these, but I do find that for this particular graph, I need them. You understand why just now? If you were, however, dealing with a shape that went up, down, there, and then across, you would have a shape here, which is a triangle on top of a rectangle, and you could treat that as a trapezium. All right, so yes, if your question here was what is the total displacement in 12 seconds, by all means do it as a trapezium, but because I want the in-between points, I've got to make sure I've got the shape. There's a question here saying, is this grade 11 work? It's actually grade 10 work. Okay, but I'm explaining it because when we do our graphs for vertical projectile motion, if you don't understand why you're doing the gradient or the area, things fall apart a bit. So I'm going through this very quickly. I'm giving myself another 5 minutes and then we've got to move on to the graphs for vertical projectile motion. So my points here are going to be 5, 10, 12, 14, and 15. This is now my graph of displacement versus time. I look at my scale here, and I've got to remember that I've got to still add in my displacement here as being 12.5. But my total displacement has to go up to 45 so that we can get in the 42.5, and I have to be prepared to start from rest. So this is where it gets a bit messy. I'm going to make this 10, 20, 30, 40. In an exam, you guys have the advantage of a ruler and lined paper and all of those things to plot accurate graphs. Please do them better than I am. So at 5 seconds, we're 12.5 meters away. So I plot my first point there. When I plot points on a graph, I plot a small dot with a circle through it so that the small dot keeps accuracy, but when you draw a line through it, you don't miss your point. Then at 10, we're at 37.5. So I'd go 37.5 as somewhere there-ish. Please, you do it a little bit more accurately than I'm doing by eye. Here we're 42.5, so I'd say that 42.5, somewhere there. 40.5 has to be above there, but below there. And then 39.5, wait, let's make 40 a little bit higher, and then 39.5 over there. Okay, so I'm just going to quickly move this one guy up so that he isn't so far out. Please, you would do this a lot more accurately than I'm doing it. The point that I wanted to make is how you now join these. This will be an acceleration, which means when we draw the displacement graph, we join it with a smiley face. This will be a constant velocity, which means when we join these 2 points, we join them with a straight line. Then this bit will be deceleration because it's a negative slope downwards. So deceleration means a sad face in. This is still a deceleration because it's got a negative slope. So I continue past there with the rest of my sad face. Can you see I've got a sad face the whole way through? This is now acceleration. So you get a smiley face. So when we draw this, we draw it in with a smiley face. All right. Okay, so Iman, when you draw graphs, you will have a ruler and I would draw them evenly spaced to scale, plotting them neatly, etc. Unless you're told to sketch. If you're told to sketch, you go wild and you just make sure that if it's bigger, it looks bigger. So 5 to 10, that 5 units should be smaller than maybe 0 to 10. Okay, so you kind of try to keep some proportion, but you don't bother measuring. All right. Does everybody understand now why I bothered with the smiley face, sad face, all of those things? It's how we join the different points of our graph together. Quick thumbs up if this made good sense. Okay, so I know this was just a quick refresher on this, but it's to make sure you understand how we can get a displacement graph. Can I please ask anyone who needs to quickly take a screenshot of this so that I can clear it? I'm going to quickly draw the acceleration versus time graph. Okay, so let's just quickly clear all of that, clear all of that, clear all of that. All right, so here I'm going to take away all of those little bits of unnecessary things that I didn't need in order to be able to answer this. Okay. Now what we're going to do, and this one's really nice and quick, is we're going to plot the acceleration versus time graph. Now remember, the acceleration versus time graph comes from using the gradient. Also, when we draw it, all of our acceleration lines are going to be horizontal lines. So if I work out the acceleration from 0 to 5 seconds, remember that's 0 to 5, no minus, it is going to be V2 minus V1 over delta T2 minus delta T1. I would throw that in once through the whole question, but you don't have to do it every time. So my final velocity is 5. My initial velocity is 0. My final time is 5. My initial is 0. So my acceleration is 1 meter per second squared. Nice thing about acceleration, it is not cumulative. If you are accelerating, there is nothing to stop you from immediately slamming on brakes. Okay, so your acceleration could go from one value to an extreme opposite value instantaneously. From 5 to 10 seconds, we save our time. Horizontal lines have a gradient of 0 meters per second squared. From 10 to 12 seconds, our gradient is going to be 0 minus 5 over, okay, because 0 is our final, initial is 5, over 12 minus 10. So it is going to be negative 2,5 meters per second squared. Our acceleration from 12 to 14 is going to be a different gradient. So we're going to end up at negative 2 starting at 0 over 14 minus 12. So that's going to be negative 2 over 2. So it's going to be negative 1 meter per second squared. And then lastly, we're going to have our acceleration from 14 to 15. The final value is 0. The initial value was negative 2. Final time was 15. Initial time was 14. So it's going to be 2 over 1, which is 2 meters per second squared. If we then plot this, we don't have to do anything cumulatively here. We're just quickly plotting the graph. So if we quickly plot this, there it is. I'm going to quickly fill in my key values here. So I've got to do something at 5 seconds, 10 seconds, 12 seconds, 14 seconds, and 15 seconds. All of these are going to be horizontal lines, and I'm going to ask you, please, I'm not drawing them neatly. It takes me longer if I use my ruler. So over here, I need to go all the way to positive 2 and all the way to negative 3. So let's make that 1, 2, negative 1, negative 2, negative 3. All right. So initially from 0 to 5, I'm going to do this in another color, is 1 meter per second. So you'd have a beautifully drawn with a ruler line. From 5 to 10 is along the axis here at 0. I sometimes make that one a little bit thicker so that you can see that it exists. Then we go all the way down to negative 2 over there, and then we jump back up here. Oh, maybe I didn't have to jump all the way back up here. We jump up to negative 1, and then here this jumps all the way up, a little bit neater there, to 2. And that is our acceleration versus time graph. Now, just something that I find is really interesting to show you here is, let's pretend I want to know what the velocity is at 12 seconds. Now you can tell here that the velocity at 12 seconds is 0. I'm going to prove it. Do you remember I told you that we had displacement, velocity, and acceleration? And that if I wanted to get from acceleration back to velocity, I could look at the area under the curve. The area under the curve here is going to be 1 times 5. The area under the curve here is 0. The area under the curve here, please just notice it's all the way down to negative 2.5, times by 2 is negative 5. 5 plus 0 minus 5 tells me that at 12 seconds, my total velocity, or my velocity at that point, will be 0. And you can actually work out at any particular point from an acceleration graph what your velocity would have been. You're unlikely to need to do this, once again, over teaching, but you'll find that because we've gone through this, it makes a little bit more sense when you're required to do less thoughtful things. All right, can I please ask everyone to quickly take a screenshot if you need to, because I'm going to stop sharing this right now. Okay, can I quickly ask who found that 35-minute revision of graphs of motion benefited their understanding of why you did the gradient and why you did the area, or how the bits fitted together? Okay, cool. All right, I know that some of you would already know this, so I'm not particularly worried that everybody didn't get it. I think some of you, I'd like to hope, had already understood it really well beforehand. So now what we're going to do is we're going to be considering how all of this applies when we are dealing with vertical projectile motion. Remember, vertical projectile motions, objects getting thrown up, dropped, etc. Okay. One of the key features about vertical projectile motion is that the entire time the object is moving, its acceleration is 9.8 meters per second squared downwards. There are no exceptions. It isn't something where, oh, when it's moving up, it's different. The entire time it's moving, its acceleration is downwards with the acceleration due to gravity. All right, so I'm now going to jump in to a summary that I've made. I usually have notes on this that are way more complicated, but I actually felt that the complications that we add to them don't really add anything. So you're going to find with every one of the graphs that I've got here, I have assumed that upwards is positive, because I find that if we deal with upwards being positive, then it makes logical sense as to what we see. So this first set of graphs, and I'm going to ask you please just to bear with me, I'm only discussing that lot for now, and then we'll scroll down to the next one afterwards. So don't jump too far ahead with what you're looking at, you shouldn't. This is an object which is thrown from one point and returns to the same point. So you can imagine I've got a ball in my hand, I throw it up, and I catch it at the exact same height that I threw it from. Remember with this that the motion is actually straight up and straight down, but if I drew it as straight up and straight down, you wouldn't see anything. So the time goes across, so it's straight up and straight down, and you can almost imagine, I have a little picture in my head where I imagine like those ECG machines in the hospital where the paper moves and the pen just goes in one line, okay? So as time progresses, the displacement changes, which is why we draw it like this. It doesn't physically mean that the ball goes forwards and up. All right, very important to note. So while the ball has its displacement, it goes up, up, up to the highest point and then down, down, down to the same position. Now, if you think about this practically, in your lesson on Tuesday, we mentioned that if an object is thrown upwards at a certain velocity v, when it comes back down to the same height, it will be traveling at negative v. So if this was upwards at 5 meters per second, when it comes down to the same point, it'll be traveling downwards at 5 meters per second. Also, at the highest point in its motion, the velocity is 0. So here is our graph. Here is the velocity, whatever this v is that it's thrown upwards with, that's its initial velocity. The final velocity will be the exact same value, but negative. So you should have an equidistant distance up here as you do down here, okay? Obviously, if this object is thrown up and it goes further down, then this line will go longer. That's not what I'm looking at right now. At the highest point in the motion, the velocity is 0. That's what happens there. And then it moves downwards. Remember here also that the gradient of a velocity versus time graph tells us our acceleration. And here we have a negative gradient. Remember, negative means down. And we in fact know that the gradient of this line is going to be negative 9,8. And in fact, we could even put in units. It's going to be negative 9,8 meters per second squared, because this is the acceleration due to gravity. because the acceleration due to gravity is constant, the gradient of this line will also be a straight line. It'll have a constant gradient. Okay? If you remember, the gradient of that line will give us our acceleration, and there's our acceleration. It's going to be downwards. In this case, I chose up to be positive. So it is going to be a horizontal line at negative 9.8 meters per second squared. Okay, so that is the case, and this hopefully gets a little bit more of an idea for you as to why the displacement graph is sad-faced. The velocity graph is a straight line with a negative gradient, and the acceleration is going to be a horizontal line with a negative value. Please note, with this particular layout here, there is nothing to stop me from making downwards positive. Then literally everything will just get inverted. But I find that those are the harder examples to deal with, and it's much easier when you get them to kind of almost turn your page upside down to see what you're dealing with. Okay, so you could imagine doing a vertical reflection going downwards to be able to make sense of that. But I'm not going to go there because it overcomplicates things unnecessarily. All right, can I ask who understood the graphs a little bit better as to how the displacement, velocity, and acceleration link? Yes? Okay, cool. Onwards. If you didn't, I'm really sorry. You're going to have to stop and ask questions in between. Okay, so we're going to scroll down to a slightly more tricky example. Not hugely more tricky, slightly. These are the kind of things you really get in the exam, so there's no point in us doing things that are too hard. This is an example where an object is thrown from a height above the ground, goes up, and then ends up going to a lower point. So this could be ball is thrown upwards from the top of a tall building. This could be ball is thrown over a cliff into the sea. This could be I hold the ball in my hand while standing, throw it upwards, don't catch it on the way downwards, and it hits the ground at my feet, which are below where my hand started. So you will notice that this graph is actually surprisingly similar to the one that we did above. The only difference is that we didn't just go up and then back down to the same height, it went lower. And what you'll notice is the difference here onwards is that it keeps going. Here, instead of us having to stop at a value, if this was V of negative V, it continues and it'll end up hitting the ground. If this were thrown upwards, let's make it at a velocity of 10 meters per second, randomly making up numbers, it may hit the ground on the route down here. It will be traveling at 10 meters per second down, which means that it may hit the ground going considerably faster, maybe at 30 meters per second, depending on how far down it has to fall. All right. So the point is that our final velocity will be a negative value because it'll be down. So velocity here means down, positive means up. Same story as before, but it'll be going faster than it would have if it only returned back to its starting position. However, nothing has changed with the gradient. Nothing has changed the entire time here. The only acceleration of this object is the acceleration due to gravity, which is 9.8 meters per second squared downwards. So these two are effectively the same thing. We could have another graph, which is where we start from here, we throw it, and your friend on the balcony catches it. Then all that you'd do is you'd draw this graph and you'd stop before you reach the same velocity on the way down. You draw the same thing here, but you'd stop because your time would be shorter. Okay, so can you see that all of these refer to the same portion of motion, up, coming down, and the difference is how much of it we look at. Okay, all right. I'm going to clear this. Please ask any questions if there are. Otherwise, I'm going to clear and I'm going to go on to the bouncy ball eventually. Okay, because the bouncy ball, I think, is the one that gets everybody. All right. Ma'am, how would you show a projectile crashing through a glass on a displacement time graph if the velocity had to decrease? So usually with an object, if there is, and they quite often recently have got a pane of glass where the ball goes up and then en route, suddenly these glaziers have appeared out of nowhere, the sheet of glass, and it crashes through the glass. Or they do, it's shot up and it goes through a tree and the tree branches slow it down. So how would you show a projectile throwing through glass on a displacement time graph if it had to? I would say that the one thing that would happen is that you'd stay at the same displacement for a little bit longer in terms of time, okay? Also, you may end up like if the object bounced off something, it could actually go back up again here. So I could have something which hits something, bounces up, and then falls down again. So you just show whether it goes up. So your question is if it hits the piece of glass and bounces up, then it goes up again. But the important thing to note is it would still be a sad-faced graph. It would still have acceleration for the rest of its motion downwards. All right. I hope that that made sense. They usually don't make you do too much with the graphs, but when it comes to the velocity graphs, that's when it gets very interesting. If it hits something, it'll have, here's a hit something graph. So it'll be going down here, then it'll hit something. It'll go very rapidly, almost instantaneously to an upward velocity because it hits something. It's a rapid change in momentum, your impulse. So there's it hitting something, and then it'll continue, but it'll still be under the effect of gravity. So it will still have the same gradient as before. So when it hits something, this is from it hitting the glass or something to immediately having an upward velocity if it bounces, and that will be the velocity that it leaves the glass moving upwards. But as soon as it's left the glass, it's a vertical projectile again, and then it'll come down again with a gradient of 9.8. All right, does that make sense? Okay, all right. Okay, perfect. All right, let's quickly clear this and move onwards. Okay, this graph is this same graph as above here. The only difference, if you notice, is instead of making the ground the reference point of 0, here I made the position where it was dropped from the reference point. So you could end up with a graph. Please, the only time you'd ever do this is if they specifically told you make the height, and then you may end up with this being 0, this being it reaches 5 meters above where it was dropped from, and the point at the bottom being, and then it hits the ground 20 meters below where it was dropped from. So we don't usually go into these unless they told you. Okay, so there's just a question, why is it not a vertical projectile while hitting the glass? Because the definition of a projectile is there's only one force acting on the object, and that is the force of gravity. When it's in contact with the glass, there's a force of the glass upwards, which causes it to accelerate because it changes its velocity. So then we're technically dealing with a collision. So it's not a projectile as soon as it's in contact with the surface. In order for something to be a projectile, it must be falling. Please, falling can even be when it's thrown up first, but it must be moving, technically falling, because even when an object's moving upwards, it is falling, but it's got to be moving, and the only force acting on it is its own weight. Okay, whether it's moving up because it was thrown or falling down, at all the times while it's a projectile, gravity is the only force acting on it. If something hits glass or hits something else, it gets slowed down or sped up by more than just gravity. All right. Okay, continuing here. So that was just a different perspective of the above one. Once again, not really relevant, but it can come up that you've got to have a different reference. Okay, and then this is just a half a graph. So I thought I'd throw this one in because it's slightly different. But what about if they only want the displacement from when the ball was thrown until the highest point in its motion? Okay, so here you can see that this object was thrown because it doesn't start with an initial velocity of 0. Just for the record, if an object were dropped, our typical dropped means that its initial velocity is 0. So typically, if you had an object being dropped, that is what your graph would look like. It starts from 0, and then it speeds up going downwards. So it would still have a gradient of negative 9.8. Okay, but the gradient would be going downwards. So this we know was thrown because the initial velocity is not 0. Just a technical thing. We could also even have it thrown downwards, where this object, if this starts on -2, this was, sorry, velocity, time. This here was thrown downwards. At 2 meters per second. All right, okay. So I'm going to quickly clear everything, quickly take any shots that you need. Quite often, this one here is one that they ask, and they even do it with the type of question that we dealt with, where we had an object that was dropped, and then a second later, we had one that was thrown. If it were a second later and it were thrown, one of the things that you'd note is that its time doesn't start at the same time. Its time here, would start 1 second later. So this could be an object that was dropped at a certain time, and this object could be thrown downwards at 2 meters per second a short while later. But the important thing you'll notice about the velocity graph is they've all got the negative gradient, negative 9.8 meters per second squared. You've got Astro in the back, busy coming to visit. Can somebody please get Astro? She's going to go and knock things. Okay. Sorry, I've got a naughty cat who has become very, very curious about the world and destroying my house. All right. Now, the last thing that I wanted to look at with you today, which is just as well, because we've only got a little bit of time left, is I want to look at bouncing objects. So when we do our bouncing objects, you're going to see here that this object starts from a certain height, and then it falls to the floor. Here it hits the floor. So that technically is a bounce. Then it moves up, up, up to a new height. Please note, we lose energy when balls bounce. So it's not going to be the same height. It's going to be a lower height because it's lost energy. Then it falls back to the ground. Here it hits the ground again. And this is the second bounce. Up to the highest point, falls down, hits the ground. Now, very importantly, at this point, and this point, all three of those, it is, okay, that one's referring to this one. It's just doing a vertical to get there. At all three of these points, when it's at the highest point, the velocity must be 0. And if you look at my picture, there's the velocity being 0, going down. There's the velocity being 0. And there's the velocity being 0. Also, we've got a situation where it is going to, now here it will hit the ground with a velocity and it will bounce up with a smaller velocity. If it hit the ground and bounced up with the same velocity because it was a completely elastic collision, which it isn't, then it would have had to go to the same height, but it didn't. So it hits the ground really hard and bounces up less hard. That means that this velocity, if this velocity goes all the way down, I'm going to make up a number here. Please forgive me. I'm not putting in any times. Okay. So if this happened to be negative 10, whatever this value here is, must be less than 10. Downwards is negative. Upwards is positive. So the ball falls down, goes faster, 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 hits the ground at 10 meters per second. When it hits the ground, it experiences a collision. Because of the force, the impulse, the force applied for a period of time, the ball changes direction from 10 meters per second down to 8 meters per second up. That's when it comes up here. It then travels up, up, up to the highest point in the motion, travels up, up, up to the highest point in the motion. As it travels up, it slows down, so that at the highest point in its motion, its velocity is 0. Then it comes down, going faster, 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 till it hits the ground. There it hits the ground. Because the position here and here are the same sides of this motion, when it hits the ground, that must be the same as that. So when it hits the ground here, that would then be at 8. So whatever value, and I've made these numbers up completely, but if that is 8, that will be the same value, because this is like the very first picture that we drew. Okay, so you could imagine that this little bit here, we looked at in isolation, just from there to there. Okay, then we've got the same thing happening here. It hit the ground, traveling downwards at 8 meters per second. When it bounces up, it's still slightly smaller because otherwise it would go to that same height. and it doesn't. It goes to a lower height. So here it's going to go upwards, going slower, slower, slower. Remember, anything that's positive velocity is upwards until it gets to the highest point over there, at which point it temporarily stops. And then it starts coming downwards, going faster, faster, faster. If this here had been, and once again, totally making this up, if this had now dropped to 6 meters per second, then our final value here will also be -6, because whatever velocity it left the ground with must be the same velocity that it returns. A couple of important things that you've got to remember from this graph. If I want to know what height above the ground the ball was dropped from, okay, I have got to look at the area under the curve. So this area under the curve here, depending on what our time is, this area under the curve equals the displacement, which will be able to tell us the height that it was dropped from. Next important thing, if we want to know the height that it reaches in any one of the subsequent bounces, we can look at either this area or this area. Same amount of distance covered going up as coming down. So either of those. Please don't do both. It's just the one up or one down. So this here will be the height after the first bounce. Okay, and then lastly in purple, if we want to know the height that it reaches in after the second bounce, that will be that little area there, or I guess we could technically work out that little area if we wanted to. Okay, so you can see each time the area gets smaller that it reaches. So this probably we should write down maximum height after first bounce, and this will be maximum height after second bounce. Last thing on this that's very important is that at all points here, the gradient is going to be -9,8 meters per second squared. You can sometimes get away without putting the units, just -9.8, because that is our acceleration due to gravity. All right, can I please ask everyone to quickly take a screenshot of that note? I think it makes a lot more sense having actually gone through what it means maybe. So the notes may get a bit confusing, but you can always come back and watch the video afterwards if there's anything that you need to go through. All right, so I'm going to quickly clear this, and then I'm going to quickly stop sharing. Okay, so ladies and gentlemen, can I quickly ask who understands the bouncing ball a little bit more than they did before? Because my experience is that the bouncy ball is what you're likely to get asked a lot. Okay, they like putting it in. And please note, even that example of the thing hitting the glass pane and then bouncing is a bouncy ball example. All right, so ladies and gentlemen, I just quickly need to ask you, please, 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 we're going to be doing a masterclass on vertical projectile motion next week, Wednesday. If you would like to earn your spot in that, please start practicing on Siavula. I really am keen to see more of you there, because I find with the masterclasses, I have a real chance to kind of go into the actual problem solving, but I can only really do that with people who've gone and practiced a bit so that they've upped their own understanding before we go there. All right.